I am Simon Clegg. Welcome to this talk about MarChemSpec, a new chemical model to constrain the impacts of ocean acidification in aquatic systems. This presentation outlines the importance of chemical speciation to ocean acidification-related science, especially pH and acid-base equilibrium, and introduces a new state-of-the-science speciation model for natural waters to be released later this year. Chemical speciation means the molecular and ionic forms that an element takes in natural waters, be it seawater, the rivers, estuaries, lakes, or brines. So, for example, dissolved carbon dioxide is distributed between CO2, H2CO3, bicarbonate, and carbonate in seawater and other natural waters. The situation for copper and many other trace metals is rather different, with a number of inorganic and organic complexes existing. And the controls on speciation are the temperature, the pressure, and the individual concentrations of all of the other species present, meaning chiefly the major ions that can be found in seawater. Why is chemical speciation important? It's important because the speciation of an element or component controls its tendency to react, affecting biological nutrient availability, toxicity, and shell building by marine organisms, for example. Consequently, a principal global ocean research priority is the question, how will the effects of multiple stressors, for example, ocean acidification, anoxia, pollution, and fishing, affect the capacity of marine ecosystems and species to adapt to changing oceans? Among the most important equilibria in natural waters, and the focus of our modelling work, are pH, the speciation of the carbonate system, and the speciation of trace metals, focusing on micronutrients and/or toxins. And it is these properties in natural waters containing the major constituents of seawater in various proportion that we set out to model. But first of all, what do we know now? What is the state of the science without the use of models? Well, for seawater pH, we have a scale for salinities greater than 20 and temperatures from about 0 to 45 centigrade. For the speciation of the carbonate system, we know the equilibrium constants for salinities of about 5 to 45 and temperatures from about 0 to 50 degrees. And these are the foundation of our understanding of ocean acidification, climate quality data. And for the speciation of trace metals, the situation is rather different. There are a variety of ad hoc approaches, and there is a pizza-based speciation model of Frank Malero and co-workers, which we are also largely adopting. Now, the bar chart on the right shows the composition of a buffer that is used to calibrate the seawater total pH scale, and the composition of the artificial seawater medium in which the buffer is mirrors that of natural seawater for the major inorganic ions. But change those relative amounts of the inorganic ions to represent some other natural water, for example, and the pH will change. So what does that leave as poorly known or understood? Well, for pH, coastal waters, which are low salinities, and estuarine waters, natural waters of non-seawater stoichiometry is of differing composition. And for speciation of the carbonate system, again, it's natural waters of non-seawater stoichiometry that are the difficulty. And trace metal speciation, by and large, most conditions, because that is the least well understood. Now, looking at the plot on the right, the solid blue area shows the temperature and salinity range for which we have a well-calibrated total pH scale for seawater. But low salinities remain problematic, and there is as yet no link to the different pH methods that are used for brackish and fresh waters. And this is a gap that needs filling. Now, it is also the case that the use of new sensors for weather quality pH really argues for new approaches, and increasingly the need for interconversion with climate quality measurements which are calibrated differently. And this requires a speciation model of pH really encompassing natural waters and pH buffers across the entire salinity range. Now, the challenge, taking as an example the bicarbonate dissociation constant K2, is to move from what we do now on the left, which is to measure K2 for every solution composition and temperature of interest, and this has been done for seawater, to move to a new approach on the right, in which we integrate previous methods with the use of models which allow us to calculate the equilibrium constants or the changes in equilibrium constants for any composition using activity coefficient speciation models. Now, the methods for doing this are proven, but they're complex, which is one reason why relatively few people try to tackle them. They do require large amounts of data, which means a lot of work, and uncertainties are hard to estimate, but that is something that we've managed to incorporate for the first time. In our project over the last several years, we have amended, tested, and evaluated a current state-of-the-science pizza-based chemical speciation model for the calculation of pH, activities, equilibrium constants, and complexation as a function of temperature, pressure, and natural water composition, including the propagation of uncertainties. Now, the left part of the slide here indicates some of the varieties of data that go into the creation of one of these models, which involves the determination of large numbers of ion interaction parameters. Now, the oceanographic applications of such a model are the calculation of acid-base equilibria, calcite saturation, trace metal speciation, all focusing on the effects of pH changes. Also, activities and complexation of core geotraces elements, iron, zinc, cadmium, manganese, nickel, copper, cobalt, lead, and aluminium, and the pH of the tris buffers used for the calibration of pH instrumentation, interconversion between pH scales, and applications in saline media of arbitrary composition. Now, we also have a program of model improvement and a measurement program that will be complete in late 2022. This is for buffers used to calibrate pH scales, to be followed by model revisions during next year and in 2024. So what has been achieved so far? One of the things we've been able to do, and this can only be done using models, is to quantify for the first time assumptions inherent in the total pH scale, which is used to monitor and measure ocean acidification. This allows us to distinguish between the operational pH in blue here, which is a scale used by oceanographers in practice, with the thermodynamic or true pH of the buffer, and to understand the meaning of the practically important extrapolation to zero buffer substance in the artificial seawater medium. And this is described in detail in some of our recent papers. Here is an example of what MarChemSpec can do, including the output as shown in a browser window. And the calculation is the change in pH and in log 10 of the carbonate equilibrium constants that will be caused by an alteration of -15% in the sodium content and plus 10% in the magnesium content of the natural water relative to a seawater of salinity 35. And you can see here the change in pH is estimated along with an uncertainty, and the changes in the stability constants also with their uncertainties here. This is a routine application of the model to a natural water and integrates with the ability to model in a self-consistent way the pH of the buffers used for instrument calibration, and also to calculate, for example, the degree of saturation of a natural water with respect to calcite and also trace metal speciation. When will the model be available? We have a program of releases planned. In winter of this year, standalone programs for Windows and Linux, and routines callable from R, from MATLAB, and from Python, and very likely a virtual meeting and tutorial. In the spring of next year, we anticipate a website for interactive calculations, and in the summer of 2023, an in-person workshop and tutorial, which is most likely to take place at Woods Hole Oceanographic Institution. Now we're working our way through a series of publications here. The first two papers on tris pH buffers in artificial seawater have been published recently in Marine Chemistry. Paper 3 on acid-base equilibria in natural waters including seawater is submitted, and paper 4 on trace metal speciation is in preparation. Now, to learn about all developments, please keep an eye on our website, MarChemSpec.org. This has the abstracts of the papers published and submitted, by the way, and if you want to join our mailing list, please contact Heather Benway at Woods Hole at this address here. Finally, we gratefully acknowledge the support of NERC in the UK and NSF in the USA for funding. The principal investigators are me, Andrew Dixon at Scripps, and Heather Benway at Woods Hole. And our measurement program is being carried out by colleagues at the National Metrology Institutes of the USA, of Germany, and Japan. And these institutes are active in this area because they have a strong interest in pH scales and in their calibration and in the production of standards. Finally, this work is a product of SCORE Working Group 145, chaired by David Turner, University of Gothenburg, and our working group, MarChemSpec, is the subject is chemical speciation modeling in seawater to meet 21st century needs. Thank you very much for your attention.